I'm Bruce Sinclair. I'm an IoT business consultant that helps leading brands, manufacturers, and enterprises define their IoT business and product strategies. In this course, I'll provide a broad overview of the technical aspects of the Internet of Things. I'll begin with an architectural overview, explaining the main components of IoT. Next, I'll explain the software-defined product. This is a digital twin of the physical product, and it's core to understanding and differentiating an IoT product from a smart product or a connected product. Then I'll discuss the hardware-defined product, the sensors, the actuators, and the embedded systems used to gather data from the physical world. Next, I'll discuss the network fabric. It joins the software-defined product to the sensors and the external sources of data. Finally, I'll discuss external systems, exploring how external systems of data can be tapped into to provide more data for an IoT product. So if you're ready, let's put on our gumboots and wade into the bits. Other than having a common understanding of technology, it'd also be helpful to have a rudimentary understanding of programming, IT networking, and data analytics. The most important requirement is that you have an interest in the Internet of Things. So let's get started. First, a definition. The Internet of Things is simply an extension of the current Internet further into our physical world, into things. Although the technology is an evolution, the business is a revolution. So when you hear all the hype, it's real. The Internet of Things is segmented by B2C, or business-to-consumer IoT, and B2B, or business-to-business IoT. B2C IoT is consumer IoT, where B2B IoT is commercial, industrial, and infrastructure IoT. In the Internet of Things, there's three kinds of products. We have our smart products, connected products, and our IoT products. In this course, I'm going to be talking about the IoT product. We've had smart products for over half a century. Simply just having an embedded device doesn't create that much value. Connected products have been around a long time too. However, it's debatable how much value is associated with just being able to connect your, let's say, dryer to your smartphone. With the Internet of Things, we can apply a lot more value to our products. The traditional engineering view has been to look at IoT similar to a networking stack, going from the media layer through the networking layer to the application layer. However, this focuses more on the plumbing. That's not where the value is. Historically, if you were a designer or a system integrator, it gets a little bit closer. There's a front end, that's for the users. There's a back end for the actual customers. And in between, there's all the enabling technology. However, I think there's a better view, looking at it from a value perspective. Before jumping too far into the tech, it's useful to start with some basics and then jump into the big picture. The business view of the IoT product segments it into four parts. The software-defined and hardware-defined product that are connected by the network fabric and interface to the external systems. The tech of an IoT product is either collecting data or transforming it into useful information. The heart and the brain of the IoT product. It is the virtual representation of the physical product. And in this case, when I say IoT product, I mean a discrete product, a system, or an environment. The software-defined product is one of four main components of the IoT product. The software-defined product sits between the interior data source, the hardware-defined product, and the exterior data source, the external systems. All three are connected by the network fabric. The software-defined product consists of two components, the Cybermodel and the application. The software-defined product is a simulation of the product's functionality. It represents, along with the analytics, all of the IoT product's value. The software-defined product is also sometimes called the digital twin because it is the virtual equivalent of the physical product. Similar to a software-defined network, we abstract the physical hardware into a software version that allows us to reorganize it and focus on what matters. The software-defined product is almost like the brain of a robotic vacuum, like a Roomba or a Nido. While at its core is still a vacuum, all the intelligence has been centralized into the brain. That is the software-defined product. The software-defined product is a key source of differentiation between the IoT product and the connected product or smart product. It is this virtualization of the physical into the digital that gives it its power. The Cybermodel is central to the IoT product as both the application and the analytics use it to generate value. The Cybermodel is one of two parts of the software-defined product, along with the application. Models are not new. We use them in computer-aided design to represent the physical representation of, say, cars. We use them in computer animation to both represent how the dinosaur looks and how it moves, and we use them in video games to represent both the character and how it operates within its environment. The video game model is probably the closest analogy to the software-defined product, with both its application and model. Think about a video game character. Their model is their personality and their skill set. The game is the application. It operates on the character, and the character acts out its personality and its characteristics within that environment. What is new in IoT is that the IoT model, the Cybermodel, is a live model, and it's also part of a closed loop, incorporating real-world data from its sensors and its external systems. The software-defined product's Cybermodel is represented with statistics. The real world is too complex to represent parametrically. Consider a simple spring. In high school physics, we would learn that it's represented by a linear equation. However, even the simplest spring, when put in the real world, doesn't behave like this. To understand how this particular spring behaves, we would apply a force to it, see how it compresses or elongs, apply another force to it, and see the same thing. Over time, we will see how it can behave. We then represent this scatter graph statistically, and use that mathematical equation instead of the linear equation typically attributed to the spring. Once the physical product is represented mathematically by the Cybermodel, it's more malleable. It can be reorganized and solved in different ways. Think about your clothes dryer at home. Once we represent it mathematically with a Cybermodel, we can reorganize it to solve for drying clothes for the least amount of time, or drying clothes for the least amount of electricity. It's important to note that an IoT product is not represented by a single model. Unlike a CAD representation, we will have many models. For the IoT dryer, for example, there isn't just one model, like, say, a CAD representation of it. We would have a model for how long it takes to dry. Along with the Cybermodel. It interacts with the Cybermodel and the analytics, which together make up the trio of value in IoT. The application in IoT provides functionality and the human and data interface. It defines the way the product works and its functionality. Thinking back to the video game example, the application is the game, and the model are the characters in the game. The application acts upon the model to create its functionality. The application is also used for communication, interfacing both with the users and the owners of the product, and orchestrating the data to and from the internal data sources, sensors, and external data sources. The application also orchestrates data to and from the model, from its internal sources of data, its sensors, and its external systems of data. In an online video game, this data flow could be coming from the sensors in the video game controllers, or from some AI being controlled by a remote data center. The application, however, is not centralized. It can be distributed anywhere on the network fabric, from the embedded systems on the end nodes to the cloud to a remote server anywhere on the internet. IoT application development is central to value creation and as such must become a core competency of every IoT company. Unfortunately, these types of products often fail because the incremental value is less than the incremental cost. Value modeling addresses this. It is a three-step process for creating valuable IoT products. Again, let's consider an IoT dryer. Our first step is to define the value proposition. In this case, it's dry clothes as quickly as possible or for as cheaply as possible while maintaining their integrity. In the next step, we quantify this value proposition. There are two parts. There's ventilation and heat. Both contribute to the evaporation of liquid into gas, which is what, in effect, a dryer does. So in this case, time, or energy, is a function of ventilation, heat, and pricing. To quantify this model, we need to capture certain variables. They could include fan speed, angular velocity of the drum, load weight, heater temperature, drum temperature, and finally, electricity pricing. These variables expose the sensors that we need to include in our IoT dryer. It's important to note that the model is not a one-and-done solution. Over time, as we capture more and more of these variables, we refine the model and it becomes more accurate. Once we have our IoT dryer in software form, we can manipulate it to solve it in different ways. For example, if we wanted to dry the load as quickly as possible, we can minimize time. We can then take those variables to configure the dryer so that it dries the clothes in the shortest amount of time. Next, we look at analytics. As mentioned earlier, the model is improved by capturing additional data points for each variable. At a high level, we can classify analytics in three ways. Looking into the past, for example, perhaps we want to do a report to see how our IoT dryer utilized energy. Looking in the present, perhaps we identify a heating coil that's overheating, so we shut down the dryer, and looking into the future, where we make predictions on, let's say, how long the clothes will take to dry. Value modeling is a key differentiator between an IoT product and its smart and connected counterparts. The smart product may have an embedded chip to determine timing. The connected product may be connected to your phone, so you can look inside or get a message when your laundry is finished. The IoT dryer can dry clothes as quickly as possible, or dry them for as low a cost as possible, and it can be connected to a network of other IoT dryers, together all contributing to a cyber model that improves all of their quality. The incremental Its purpose is to capture data from the edge, sometimes process it, and then transmit the data over the network to the application. Because of the nature of an IoT product, the edge can be within the product or distributed across the system or environment. The hardware-defined product consists of two types of components: connected sensors and actuators, and an embedded system. The hardware-defined product only includes these two components and not the rest of the physical product. The sensor gathers data from the physical environment. The actuator makes physical changes to the product. The embedded system gathers the data, packages it, and then sends it along the network to the application. It may also do local processing of the app, analytics, or security. The hardware-defined product captures internal sensor data and transmits it over the OT, or operational technology network, to the software-defined product where it's processed. It's accessing them from the internet. Regardless of data needs, there will be a sensor available to capture it. It's important to note that value drives sensor selection. Value defines the information that's required. The information defines the data that must be captured, and the data that must be captured defines the sensor that must be used. The challenge is finding the right one. Selecting a sensor is the first step. Before implementing a sensor, it's important to invest some R&D time to test and verify the specifications. The transducer on a sensor converts the physical world into a DC current. This energy is then converted by an A to D converter into a digital payload. Actuators work the other direction. A digital signal, which is really a message from the application, is converted with a D to A converter to affect the physical environment. Going back to our IoT dryer, we may use an actuator to increase the fan speed or decrease the temperature of the heating coil. To make a sensor a connected sensor requires an embedded system. The embedded system takes the digital payload, packages it, and sends it along the OT network to the application. All incremental value from an IoT product comes from transforming its data into useful information. Sensors are one of the two main sources of data in IoT. They're mostly responsible for connecting sensors to the internet. Remember, an IoT product is a discrete product, a system, or an environment. An embedded system, sometimes called an embedded chipset, is a dedicated computer system that lives on the edge of the network. Instead of a CPU, it runs an MPU. And instead of a traditional operating system, it runs an RTOS, otherwise known as a real-time operating system. The embedded system, or chipset, may include radios and sensors. The purpose of the embedded system is to manage communications between the sensors and the OT network, taking the data load from the sensor, wrapping it into a protocol, and sending it along the OT network. The embedded system also stores and executes local applications, analytics, and security. Embedded systems primarily package data to be sent on the network, but increasingly we're seeing the emergence of miscomputing. That is, computing on the edge to run the application, analytics, and security, both of which are provided by the embedded system. The connected sensor requires both the sensor and the embedded system. And this is the same architecture that's used for actuators. Bringing it all together, the connected sensor consists of an MPU, I/O interfaces, power, and optional radios. The sensor consists of a transducer and an analog front end, or the actuator and the digital front end. There are two main configurations: standalone connected sensors and connected sensor arrays. A standalone connected sensor consists of a single embedded system with a single sensor, and it's added to existing products. Connected sensor arrays are one embedded system with multiple sensors. These are used in new products. For example, in our IoT dryer, we would use a connected sensor array. Standalone connected sensors are generally used in commercial, industrial, and infrastructure IoT to add an overlay network to an existing product that's too costly to replace. Connected sensor arrays are generally used in consumer IoT and in new business IoT products. Its main job is to transport internal data from the hardware-defined product and external data from the external systems to the software-defined product. It consists of the OT network, that is the operational technology network that's inside the product, the IT network, or information technology network, that takes the data to the cloud, the backhaul, which is the uplink, the internet, and the product cloud, which is a private computing resource for the product. However, the network fabric is more than just connectivity. It's called fabric, but in fact, it's a distributed computing platform. As well as networking, it provides computing and storage. The languages that allow the different part of the network to talk to each other are called protocols, but this is equivalent to standards or sometimes referred to as layers. Especially in the operational technology network, these protocols have evolved separately and to their own purposes. They started as just communicating with screens, then between machines, and finally within local area networks. There are three main protocols in IoT. The media layer is first. It organizes the information to be transmitted by radio. The second is the networking layer. It organizes information to be transported along either the OT or the IT network. And the third is the application layer. It provides contextual data along with the data payload to be consumed by the application. And fourth is the media layer. It's not standardized yet, but it constrains the vocabulary that's used in the application layer. It's useful to think of IoT protocols as nested Russian dolls. First, we have our payload. This comes from the sensor. It is wrapped by the application protocol that has extra information to provide context to the payload. Wrapped around the application protocol is the network protocol. This gives the network the information it needs to move the data along the path. And finally, we have the media. Its main job is to move data from the sensors to the backhaul that takes it up to the internet. The OT network is operational specific. It supports the product or the company's operations. These networks have grown individually to support the various industries in which they're found. Their job is to connect the sensors and the actuators. However, they are usually proprietary. These networks are generally in the product itself. Now remember, the product can be a discrete product, a system, or an environment. Therefore, they can be a personal network, a local network, or a wide area network. From a hardware perspective, they consist of gateways. This is negatively referred to as the Internet of Gateways. There are hundreds of proprietary protocols in the OT network. Protocols for automation, industrial control, building, power automation, automobiles, homes. They're all different and all have been designed specifically for their purpose. The second half of the FOG is the Information Technology Network, or IT network. Bridging the OT network and the IT network is the radio. These radios can take the form of Bluetooth, Wi-Fi, cellular, LPWA, or others. The connection between the IT and the OT networks is generally wireless, but Ethernet can be used. The IT network's job is to move the data from the receiving radio to the backhaul uplink to the internet. Let's consider our IoT dryer. Data from the sensors are carried across the internal network. This is the OT network. They are then transmitted over the air using Wi-Fi. The IT network is a small network in your home between your router and eventually the fiber uplink that leads it to the internet. Hardware in the IT network used in the Internet of Things is the same as the hardware used in the Internet of People. Routers, switches, firewalls, the technology is the same because the network is the same. The IT network has been standardized on IP, that is Internet Protocol. This is a major benefit over the OT network. It is a benefit in terms of cost, implementation, but also this provides an attack vector. The problem is the seam between the OT network and the IT network needs to be translated by a gateway. This gateway is a favorite source of attacks. Over time, we will unify the FOG with one protocol. That will be the IP protocol. The IT network is getting closer to the data source and will eventually replace the OT network protocols. The trend in the Internet of Things is to move computing closer to the data source. The private cloud expands the product's computing, memory, and storage capabilities. It is different than the IT cloud in both technology and business. Technically, the IoT product cloud must support different application protocols, different analytics packages, and different development environments. It must also support the APIs of different data services that may not be used in IT networks. More profoundly, the business model of the IT cloud must change. In IT, there are fewer users that are using a lot of bandwidth. In IoT, there are many users using less bandwidth. Applying the IT business model to the IoT architecture doesn't work. Consider the computing power that can be harnessed for any product. If needed, the IoT dryer, for example, could use an entire data center of servers to provide amazing functionality, much of the network fabric required by the IoT product. Structurally, an IoT platform is middleware. It consists of the IoT product cloud, the IT network, and sometimes part of the OT network. In some cases, it includes a development environment. There are three main forms of IoT platforms. First, we have the Application Enablement Platform, or the AEP. As the name describes, it is a more holistic platform that allows the manufacturer to develop their application within the context of their networking. The second type of IoT platform is called the Provisioning Platform. It has history in M2M and telematics. Its primary purpose is to provision a SIM card to establish a cellular connection. The third type of IoT platform is called a Connectivity Platform. It is a subset of an AEP, and it simply establishes a connection between a software module on the embedded system and the Internet. This is generally what connected products use. When using an IoT platform, consider the risk of building your application on rented LAN. Develop it in a modular way so it can be moved to a different platform. There are two main IoT platform architectures. The first is a publish and subscribe architecture that uses messaging. Generally, this is easier to implement, however, the time of data delivery is less predictable. The second architecture is a client-server architecture. While a little bit more complicated to implement, it can be used in more real-time applications. Most, if not all, companies they include all the sources of data on the Internet that can be accessed by an API. There are four main components to external systems. The first one is analytics, where data is transformed into information. The next is data services. These are sources of data available on the Internet. Business systems provide internal operational data that could be useful to the product. And finally, the last source of data are other IoT products. It is this interfacing with these external sources of data that differentiates the IoT product from the connected product and the smart product. Just like any other software on the Internet, the virtualized IoT product can interface with these external systems the same way. This opens up massive amounts of functionality previously available only to software, and in doing so, changes the definition of what a physical product is. All incremental value from an IoT product comes from transforming its data into useful information. External systems are one of the two main sources of data in IoT. A classic example of statistics is linear regression, where a line is fit through a bunch of data points. But linear regression is also considered a supervised machine learning, or ML, algorithm. So is linear regression statistics or machine learning? It's both. If it's a static one-time event, it's statistics. If you're training a model with one data set to be used to make predictions about another data set, and if the model is continuously being improved with new data, and if the data sets are huge, it's machine learning. The trick in data analytics is to find the right model and then model its parameters, coefficients, and constants to improve the results. We can manage things if there are just two parameters. But if there's hundreds of parameters, which is often the case, or even hundreds of thousands of parameters, as found in deep learning networks, then we need machine learning to tweak the parameters, the coefficients, and constants. Machine learning is simply statistics wrapped in learning software that tweaks the model's parameters to make it more accurate. Today's large data sets necessitate the tight integration of statistics and learning software. So although purists are technically correct when they say that not all analytics is machine learning, it's easy to understand why people use the terms interchangeably. Another way to classify analytics is by what it does. Analytics and ML identify things, like using facial recognition and speech recognition. They predict things, like predicting the effectiveness of a vaccine. They group things together, like when used in spam filtering, and they associate things, like when used for medical diagnoses. And yet another way to classify analytics, or in particular machine learning, is by how it learns. There's three types of learning software. There's supervised learning. That requires the datasets to be labeled, so the software can learn when it's right or wrong. This is used when identifying things and predicting things. A good example of this is teaching cars to identify things on the road using deep neural networks and learning the warning signs for a jet engine predictive maintenance system. The second learning software is unsupervised learning. Unsupervised learning only needs raw data. It is used for grouping things or associating things together as data microservices are abundant on the internet, and until IoT, were only accessed by software. Data services such as weather, mapping, and pricing can provide incredible value to physical products. Many data services are free, some are not, but what they have in common are they're all accessed with an API. Once our product has been virtualized, it too can call APIs, just like software. Consider IBM's transformation from once an infrastructure company to a software company, and then a professional service company, and most recently with their acquisition of the weather company and their increased emphasis on Watson, they have now become both a big data and analytics company. Weather isn't the only data IBM is analyzing. Watson is being used in consumer, commercial, industrial, and infrastructure IoT. The transformation of IBM clearly demonstrates where all companies should be heading. Since the IoT product is virtualized in the software, it can interface with this rich form of data in the same way that internet software does today, through the automated collection of business intelligence. Now IoT products can interface directly with business systems, circumventing the need to manually input and extract data. Interfacing products directly with the CRM system, or Customer Relationship Management System, enables the enterprise to track customer requirements and needs. If, for example, a tire manufacturer senses tire tread, they can notify the fleet manager when a tire is becoming unsafe and offer them a deal to replace it. Interfacing products directly with the PLM system, or Product Lifecycle Management System, can track product use and use this information to prioritize future features. If, for example, a lot of customers use their smartwatch in the water, a manufacturer may prioritize the development of a water sports version. Interfacing products directly with the supply chain management system can follow their progress through the entire supply chain. For example, since Tesla cars can be ordered online, the company can track each car from the time of order through manufacturing to delivery. Interfacing products directly with an ERP system, or Enterprise Resource Planning System, enables enterprises to track workforce efficiency. For example, a smart factory can track how long each worker uses each machine. Through analytics, the enterprise can determine its most efficient staffing. This direct interfacing with business systems be connected to each other like Lego blocks to deliver outcomes. The IoT platform is a technical underpinning that allows one product to be connected to another. Over time, that product will develop into a family of interconnected products. When companies can orchestrate their products to work together, they can deliver their customers' outcomes. One way to quantify the value of multiple connected products is with Metcalfe's law. Metcalfe's law states the value of a network increases exponentially with the number of its sources. Since each product is a data source, value goes up exponentially in proportion to the size of the product network. This together leads us to the outcome economy. Like with Legos, the more parts to the system, the more value there is. But there's a couple points I'd like to reiterate. The software-defined product is the heart of IoT tech. It interfaces the physical into software that can be then interfaced with the internet. All incremental value of an IoT product comes from transforming its data into useful information. When designing IoT tech, think top-down. Start with value. That defines the information that's required, which then defines the data that's required. Only then is technology considered. To create an IoT product, there's still a few other areas that need to be considered. IoT security is very important. It needs to be considered at every step of the development cycle. Analytics and big data are also very important, as they're key to transforming data into useful information. Standardization is still evolving in IoT, so protocol analysis must be understood. I only covered value modeling at a high level, but it's core to designing a successful IoT product. Creating a successful IoT product requires a full picture. You can start with my IoT Foundations, Monetizing IoT, if you want to learn about how to make money with IoT. Security is really important in IoT. There's a great course introducing the concept called Securing the IoT Introduction. And if you want to dig deeper into programming IoT, there's Programming the Internet of Things with Android and Programming the Internet of Things with iOS. If you'd like to check out my book that this course is based on and the other services I provide, go to my website. And if you want to learn more about IoT, head on over to my media site. There you can listen to podcasts, watch video interviews, and read articles from other IoT leaders.
Even cities are using technology to improve transportation, waste management, health, and public safety. Well, these are just a few examples of the power of the Internet of Things, or IoT. And this concept is becoming part of our daily lives and rapidly changing the way we interact with the world around us. In this LinkedIn Learning course, I'll give you an overview of the Internet of Things, covering definitions, architecture, components, and ecosystems. I'm Zara Khalil. Join me as we explore IoT together. Standards and ecosystems. No previous knowledge is required, as I will take you through an overview covering IoT definitions, IoT components, standardization process, and I will go through examples when is covering IoT in industrial automation, a specific area, and when covering IoT example in wider perspective in community as smart city. It's mentioned in 1999 during a presentation on supply chain management at MIT by British technology pioneer Kevin Ashton. Earlier forms of communication within IoT often involved machines of the same type, called machine-to-machine or M2M communication. For example, the devices used in supply chain management systems to track inventory where all communication is done locally. Today, the Internet of Things has expanded beyond machine-to-machine communication. Devices of all types can communicate with each other from anywhere in the world. This can include large-scale industrial applications like SCADA systems, commercial products like smartphones, or local networks of sensors like traffic monitoring systems. There are two common term definitions used to represent the concepts regarding IoT environments: Internet of Everything and Industrial IoT. Internet of Everything is used by Cisco to refer to the intelligent connection of people, processes, data, and things. That includes machine-to-machine communication, machine-to-people, and technology-assisted people-to-people interaction. Industrial IoT IEEE defines the Internet of Things as a network that connects uniquely identifiable things to the Internet. The Internet refers to the large category of applications and protocols within the network. The things are basically any device that is capable of connecting to the Internet, including smart devices, sensors, daily personal devices, factory machines, and any other entity that's able to communicate with other connected objects. Information about the things can be collected and their state can be changed from anywhere, anytime, by anything. This also includes people who operate the devices and use the applications. So the relationship is people to people, people to things, and things to things. IoT as a concept is simply connecting devices or things to the Internet and or to each other. IoT encompasses the following fundamentals: smart sensing and actuating, computing, and connectivity and communication. Billions of smart things connected to the Internet, so compatibility is important. Incompatible protocols can become an issue, meaning the integration of data and services from various devices can be complex and challenging. This introduces the Web of Things, or WOT. The Web of Things describes the integration of different objects of the Internet of Things to the web to enable communication between heterogeneous devices and objects. The Web of Things emerged as an application platform of the Internet of Things. It was created to overcome the lack of interoperability of the Internet of Things across some platforms and develop a standard to have a common platform for IoT. The things within the Web of Things have smart embedded systems that enable communication with each other or with the web using the existing web standards. And by having a universal application layer protocol, this creates an open IoT ecosystem where all objects,
devices, and applications can easily connect and talk to each other regardless of how they are physically connected.
It's based on the Open Systems Interconnection or OSI model. The OSI model was introduced by the International Organization for Standardization, or ISO, in 1984. It is a 7-layer model: physical, data link, network, transport, session, presentation, and application. Each layer provides services to the layer up or down the stack. OSI is a reference model of how components can communicate over database networks. Usually, the IoT architecture is divided into subsystems. The generic model has 3 layers: physical, communication, and application. Physical layer consists of the hardware objects to sense the status of things, such as sensors, actuators, human operators, computers, and smartphones. The second layer is the communication and network layer. Includes the different communication methods and standards that are applied between the devices and the back-end services. The third layer is the application and service layer. This includes examples like event processing of the data, healthcare management, and environmental monitoring. These 3 layers are considered by the IEEE P2413 standard as the fundamental IoT architecture and can be used as a reference model for any actual IoT system. Here's an example. The first layer, where data is collected, then using communication to transfer the data, and finally for data analysis. In the IoT architecture model, the data flows in both directions, from the physical to application layers and vice versa. A complete IoT architecture has a flawless operation of its components and reliability within its design. The IoT architecture is unique for each system. It depends on the different devices utilized, the communication methods, and the services and applications the system is used for.
Hardware and software. These components communicate using a wide variety of protocols. Hardware refers to the physical devices that are used to collect and present data, like sensors and actuators, such as temperature, proximity, pressure, and humidity sensors. Or hardware devices used to present data like desktop, computers, tablets, and cell phones, and human-machine interfaces for industrial applications. Hardware also includes standard network devices like routers and switches, as well as the devices used in the application layer or back-end applications, such as monitoring, data processing, smart traffic, and personal healthcare devices. IoT devices are capable of analog to digital conversion, collection and generation of data, remote connection, which means the ability to be controlled over the internet, real-time monitoring, and device safety for data security. The second component is software. IoT software is the set of programs which enable data storage, data processing, data transferring, and data analysis. Also provides data collection, data integration, real-time analysis, optimization, and communication protocols. IoT software also connects the hardware devices
adopted IoT. Within healthcare, IoT has been used to enhance patient quality of life, improve safety and security, avoid unnecessary healthcare costs, and provide the right medical support at the right time. An example of an IoT application within healthcare is a health monitoring system for elderly patients. In general, the system consists of having body area sensors that collect biological data, microcontrollers to collect data from the sensors, gateways send the data to a local or remote location using wireless or local network, The destination could be a simple computer software program used for monitoring, tracking, and analyzing data by a healthcare provider. Here is an example of a health monitoring platform by Empatica. The wearable medical device collects and streams vital signs to a user-friendly app and web dashboard, where data can be accessible by healthcare providers to decide whether an intervention is needed. Now, since the healthcare monitoring system provides accessibility to different users, for example, different healthcare providers, the patient themselves, and/or any family members or caregivers. So one of the challenges of using IoT within healthcare is providing data security and privacy. Security can be achieved physical, communication, and application. So using our example of the health monitoring system, the physical layer includes patient body sensors, microcontrollers, network devices, and any medical device in the system. This also includes the computers or devices used to display the collected data from the sensors. The second layer includes the communication protocols of the networks used to transfer data from the sensors to a back-end destination, like the internet or the local area network. The third layer is where data is received for analysis or monitoring. It could be an app within a smartphone, computer software, or a data control center application, software and hardware. So for the automatic monitoring system, examples of hardware components: sensors used to evaluate patients' vital readings, computers and smartphones, microcontrollers, and network devices. The software components are the operating systems, virtual machines, communication protocols, and data analysis software. On the physical layer, as a matter of fact, sometimes they are merged, as in this common example of an IoT system used in our daily lives. Here is a smartwatch monitoring heart rates. The physical layer includes the smartwatch and the smartphone device. The communication layer is the wireless internet connection, and the application layer is the app inside the phone. So the device itself is the physical layer, and the app inside the phone is the application layer. An example that is used daily is Apple Watch. Apple Watch is a smart device. One of its applications is heart monitoring. The heart rate can be checked from the device itself or using a smartphone app. The app is called Heart Rate App. Networks of sensors and smart objects whose purpose is to interconnect all things. The IoT ecosystem is a little bit harder to define because each example is different and each system contains a wide range of objects, including different devices, apps, services, and networks. So to have a general overview of the IoT ecosystem, we can divide it into three main areas: IoT technology, IoT market, and IoT standards.
The fuel for the growth of IoT ecosystem. The fast development of the technology in different areas made a great impact in expanding of the IoT ecosystem. For example, an early IoT ecosystem would include a machine and a monitoring unit connected through a network within one location, like factory floor. Now, an IoT ecosystem can involve thousands of objects on a larger scale. An example is smart city. Technology includes the development of network and communication, includes computing and storage within the wireless communication, or network coverage like 3G, 4G, and 5G. Technology also includes smart devices like the ones used in smart homes and daily activities, or sensors, actuators, and devices used in industrial and manufacturing processes. There are things that need to be considered within IoT technology. First, testing and validation, and second, enable multi-system integration. The technology within IoT depends on the interoperability of the different devices. So testing provides the assurance that the different devices within the IoT
places where IoT systems are used, physical or virtual, and what fuel the development of new IoT applications. The market for IoT is global. Here are a couple of the common players that contribute to its growth: commercial and retails, research and academia, government and utilities, and business and innovation. One of the common examples of IoT in retails is e-commerce or online shopping. In retails, an example of using IoT solution is enabling a full and easy shopping experience for customers by using different user-friendly apps and providing smart payment solutions. Using IoT not only improves operational efficiency, but also enhances the customer experience to gain competitive advantages. The IoT in commercial market has two categories: online and offline. The online, like the different apps and websites used for online shopping. The offline includes manufacturers producing smart appliances, building automation devices, and personal devices. Research and academia contribute to IoT market. Research means creating the theories, new products, and materials for IoT growth. The research can be done within academia or research centers within government and companies. In academia, IoT has been implemented in the form of e-learning. Many educational institutions
Government and utilities. Government can help in shaping IoT markets and technology through fundings in areas like energy, defense, security, education, and transportation. Utility also contribute to the IoT market. Examples of utilities include smart cities and smart grids. This includes the IoT devices used within the city environment, like traffic cameras, security cameras, smart meters, smartphones, smart home automation, and cloud intelligent networks. Business innovation is another major player in the IoT market by developing new products and services using IoT technology, as seen in commonly used products ranging from smartwatches to transportation services like app-based ride-sharing. Innovation is also notable in healthcare systems, where devices are used to help patients and healthcare providers, like monitoring systems, tracking sensors, and smart healthcare apps.
IoT standards. Standards are published documents that include specifications and procedures. IoT standardization is the cooperation among industry, customers, public authorities, and other interested parties for the development of a technical specification of IoT applications. There are different regional and international standards organizations that work on producing the IoT standards. Examples: Institution of Electrical and Electronics Engineering, International Electrotechnical Commission, International Organization of Standardization, International Society of Automation, and the Internet Engineering Task Force. There's a specific and separate IoT standard for each area. For example, energy management, information technology, communication and networks, health, and education. Here are a couple of examples of different IEEE standards. IEEE 11073 is a standard used for health and medical device communication. IEEE 802.11 is one of the standards for Wi-Fi. IEEE 2413 is a standard defines an IoT architecture. Another example is International Organization of Standardization. ISO standards that are related to IoT are developed as a collaboration between ISO and IEC. An example is ISO/IEC 30141. This standard
common norms and regulations for the development of a technical specification. Standards organizations are grouped as national and regional or international. National standards apply only to the country or region in which they are formed. National standards may be government-sponsored or independent. International standards are generally applicable everywhere. Some examples of national standard organizations are American National Standards Institution, National Institution of Standards and Technology, and Standards Council of Canada. Examples of international standard organizations include International Organization for Standards, International Electrotechnical Commission, and Institution of Electrical and Electronics Engineering of Standards Association.
This organization has a unique name format. The name of IEEE standard starts with IEEE and a number that represents the family of standards that is grouped together of the topic selected, and the year the standard was established or approved is added at the end. The family of standards is 2413, and this standard was established in 2019. The standards of the International Organization of Standardization, or ISO, that are related to IoT are usually developed as a collaboration between ISO and IEC organizations. An example is ISO/IEC JTC1. This standard was developed for information and communication technology. The name represents the two organizations that work on the standard. ISO and IEC have established a joint technical committee. It is called JTC-1, which stands for the Joint Technical Committee. The committee members are the people who develop standards to codify certain guidelines. Each standard is defined by a distinguished name. This represents the organization, committee, and subcommittee. The standard name that deals with Internet of Things within ISO organization is ISO/IEC JTC1/WG10. The name explains the standardization hierarchy. ISO/IEC, the joint organizations, JTC1, Joint Technical Committee, WG10, Working Group 10, which basically the team working on IoT standardization. Another example is the standardization that deals with involved in developing standards are initiation, proposal, preparation, committee meeting, approval, and finally, publication. The time from the first proposal to the final publication usually takes about 3 to 4 years. Organizations may follow slightly different methods, but generally, they all follow the main development stages to establish a new standard. The first step is initiation, also known as the pre-selection, which involves identifying and researching concepts related to the new standard. The idea or concept can be broad or very specific. In the pre-selection stage, the group and the sponsor that is requesting the standard development usually provides technical oversight for the standard that helps to determine the scope and the nature of the technical content. The second stage is a proposal. The proposal develops a layout for the required information. The proposal is done by submitting a project official request after identifying a need for a standard. Each organization has its own method and a protocol for the submission request form. This applies to the national, regional, and international organizations. The third step is preparation. During this stage, research of the basic guidelines is performed. Preparation of the first full draft is completed. One of the ways to start the preparation of the standard is to break the document committee meetings. During this stage, committees meet to work on and finalize the draft of the standard. Each group that was assigned a task can officially begin its work to develop and write the standards. The committee usually involves working groups, content development team, and professional staff of editors. During the committee meetings, the draft of the standard is discussed, and the committee can then comment and vote. Also, the draft is shared with the members of the organization committee. At a national level, committee meetings are open for all interested parties, and document drafts are also made available and usually reviewed periodically. In cases where there are an international standards committee working, these documents can be submitted to the international organization for international committee approval. During this stage, a vote on a draft standard by the committee members occurs. While anyone can contribute and suggest comments, the only votes that count toward approval are those of the eligible members of the balloting group. The voting time varies for each organization. For example, the ISO organization usually takes 8 weeks vote. For IEEE, it usually takes 30 to 60 days. According to IEEE, a standard will pass if at least 75% of the ballots from the balloting group are returned, and if 75% of these are yes votes. After approval, the standard is given a final review by the members of the working group before it gets published. An editorial check is also needed. The role of an editor is to ensure that the standard is grammatically and syntactically correct. The final stage is the publication. Here, after the approval stage, a standard is made available for all users. At the publication stage, only editorial corrections are made. No changes are made to the content or to the technical meaning of the standard. According to IEEE, a standard is valid for 10 years from its approval date. During the 10 years period after the standard is approved, a working group can develop revisions or extensions to the standard, and each revision or extension must go in 2014 that focuses on topics in IoT, creating a variety of related standards. The IEEE IoT initiative serves as a platform for professionals to collaborate on research and development standards. It also serves as a reference to the global community of professionals working on technologies related to IoT. Many of the IoT standards within IEEE are set by the IEEE Standards Association, IEEE-SA. Another IEEE group that develops standards for IoT is the IEEE Communication Society. The IEEE 2413 standard is directly related to IoT. This standard defines the architecture framework for the Internet of Things, including description of the various IoT domains, and provides a reference model that defines relationships among various IoT systems, and it includes details about protection, security, privacy, and safety. This standard status is active, which means it's still being developed and updated as of the recording of this course. The last version that was published was in 2020. The standard development team consists of the following. Working group is IoT Architecture. Standards Committee, BOG, which stands for Board of Governors, /CAG, stands for Corporate Advisory Group, and the society is IEEE Board of Governors. Here are a couple of examples of IEEE IoT-related standards. P1451 is focused on developing a standard for harmonization of Internet of Things, devices, and systems. IEEE 25110 covers the quality of data sensor parameters within IoT. This standard provides a reference architecture for smart city. A very common IEEE IoT standard is the IEEE 802 family of IEEE standards dealing with local area networks. It consists of 71 published standards with 54 under development. The most widely used IEEE 802 standard
The first is settling on a common definition of IoT that easily identifies its components. The need to have global reach and coordination between stakeholders is very important, as it saves time and effort within the different organizations that work on the development of standards. Also, agreement on the architecture and reference models used within certain areas, like data transmission, energy, or transportation, is critical. Finally, scalability, which means that the developers of standards need to keep in mind that these standards can be applied widely to different regions. Security, privacy, complexity and standards, and legal issues. For security, due to the fact that the scale of IoT applications, devices, and services is large, the quantity of connections between these devices is large as well. Therefore, the users of the systems need to trust that the information and services are being exchanged in a secure environment. This is very important as IoT technologies become more integrated into our daily lives, and poorly secured IoT devices and applications make them a potential target for cybersecurity threats. Rarely a day goes by that we don't hear about another cybersecurity attack. Not only businesses and governments are the target, but also regular people through any of their personal devices. Things like hack, data breach, or damaging malware. So on a personal level, here are some suggestions. Choose a strong, unique password that you don't share with others. Also enable two-factor authentication, means that you need to enter not only a password, but also a one-time code that's sent usually to your mobile phone. In general, here are some of the methods used to make IoT systems more secure. Have a general attack detection and recovery system that's Having a large network of devices and applications, IoT systems are designed to collect sensitive data about their environment and oftentimes data related to people. To help IoT systems ensure privacy, cryptographic techniques can be used that enable sensitive data to be stored, processed, and shared without having the information content accessible by outside parties. Another consideration is during the design process of the IoT devices or systems. This simply means the need to have a plan to ensure that the IoT device itself has the required privacy layers. Regulations are also needed when collecting data involving people. This can be done by having fair and consistent rules that help apply privacy, protection, and transparency within the IoT ecosystem, and ensuring that personal information is being protected by the collector. Now, there had been many incidents involving privacy breach. An example is with Yahoo. In 2016, the company first publicly announced a privacy breach incident, which it said took place in 2013. Yahoo announced that the actual figure of user accounts exposed was 3 billion. Yahoo suffered a second attack in 2000. Complications with an IoT ecosystem can be found in the design, deployment, and maintenance of devices due to the fact that IoT systems include the use of multiple technologies and large set of components. Complexity can also include the variety of user requirements and preferences. The fourth challenge within an IoT ecosystem is interoperability and standards. Interoperability is the flexibility of an IoT system to integrate easily with another system without conflict due to the different heterogeneous IoT protocols. In a fully interoperable environment, any IoT device would be able to connect to any other device or system and exchange information as desired. Standardization helps make it easier for devices to talk to each other. The first challenge when it comes to standardization is that some device manufacturers limit their interoperability of the devices and components within the same manufacturer. And that makes the communication part quite difficult to be applied if these products were used with different vendors. Another challenge is that due to the globally competitive market, some IoT device manufacturers try to get ahead and take advantage by bringing a product to the market quickly without having the proper standards in used to collect user data and transfer the data to another place for data storage, assessment, or analysis. Using sensitive personal data in this way can quickly become a legal issue. The main concern is that these data might be used by other parties for both beneficial and discrimination purposes, like health insurance, commuting, travel information, and so on. Consider using IoT devices for public safety, like surveillance cameras. An example is UK. The UK has a reputation around the world for being one of the highest users of surveillance cameras. An estimation is between 4 to 5.9 million cameras. Concerns were raised as this puts the privacy of the public at risk of being invaded on a mass scale without its consent, due to the collection of big data with the integration of video surveillance. And couple of key questions are: who become responsible for the footage, how long to keep it, and how to ensure the proper secure data storage and protection. These scenarios and others raise a question about the legal consideration for the IoT devices and data collection. Now, this takes us to the question of whether standards need to specify the design requirements and customer protection regulations pertaining to the data generated by the IoT device. However, sometimes having strict regulations can limit interoperability between devices used within an IoT ecosystem. So, while we can enjoy the applications of Internet of Things in I will cover two examples. First, we will take a look at an IoT in industrial automation ecosystem, a specific area, and next, how IoT systems work in community in smart cities. Industrial automation refers to the environment of industrial systems, manufacturing, chemical processes, power generation facilities, oil and gas, or any factory settings related to industrial applications. This includes, but is not limited to, computers, robots, machines, sensors, actuators, network and monitoring devices. There are three main levels within industrial automation systems: field level, control level, and management level. The field level includes all the devices used within the field. The control level includes the different types of controllers, such as PLC, that is used to control the design process. The management and information level contains the logic and design element of the system and any monitoring applications of the process. All these components communicate using a local network or internet to exchange data between the components, creating a industrial IoT or IIoT. Industrial IoT focuses on industrial processes and workflows. This encompasses IoT ecosystems and applications used within industry. In literature, it is defined as the use of Internet of Things in smart manufacturing. That refers to the interconnected sensors, controllers, and other devices networked together in an industrial setting. It also incorporates machine learning and big data technology. The industrial Internet of Things enables the gathering of excessive amount of data from production lines, factories, electrical and energy systems, as well as building management and automation systems. Industrial IoT allows for remote access and monitoring, data acquisition, collection, exchange, and analysis. The industrial IoT has numerous potential benefits: improve productivity, safety, maintenance, reduce costs in production, increase operational efficiency, and increase uptime. Regulate each level of the industrial automation system. A very common IT standard is IEEE 802. It is used within the management and application level to connect multiple devices or controllers. There are also Ethernet-based industrial networks like Profinet, Industrial Ethernet, and Ethernet IP. Ethernet is known for its large data capacity and for its ability to support multiple communication protocols on the same wire. One of the common Ethernet-based standards for communication in power generation facilities and substation is IEC 61850. This standard regulates communication between different equipment located in a substation, such as protection, control, and measurement equipment, as well as intelligent electronic devices or IEDs. For field level, couple of the network standards for sensors are DeviceNet, Heart Communication, and Profibus Protocol. Another example is the IEC 61158 standard, which regulates industrial communication networks field bus specifications. Here are examples of some IEEE IoT standards used in the robotics and automation space. Here are some examples of standards used for industrial IoT and smart manufacturing. You can see here examples of factories are now faster, smarter, and more efficient. Every aspect of the manufacturing process is monitored, evaluated, and enhanced through the use of industrial IoT. In a smart factory, we have sensors and devices that communicate with each other. Data are exchanged in real time using secure network connections. Monitors are used within the field or in controlled rooms, or remote monitoring using wireless communication. The data generated from the sensors are collected, then transferred and stored in the cloud or data center for monitoring and performing data analysis. The data analysis helps in sensing out-of-spec conditions. An example: if the temperature of a piece of equipment exceeds specifications, the sensor can detect this and send a signal to stop breakdowns before they occur. Data analysis also helps in reducing scheduled maintenance. Machines used in smart factories can send repair alerts and preventative maintenance reminders to allow maintenance to be performed as needed. Big data analytics help in management as well, including monitoring inventory and tracking parts as they move through supply chain. Forecasting manufacturing process time that helps in improving efficiency and process optimization. There is no doubt that there are great benefits of using IoT within factories, and one of the visions of Smart Factory is to be able to have a fully automated system. Now, this may raise the question of replacing humans with robots and depend fully on machines. Also, while IoT in factories can have advantages of increasing level of productivity, this can also multiply the potential vulnerabilities and risk of data breach been integrated in our daily lives. The smart city concept involves the implementation of IoT technology in many of our daily activities and interactions within the city, inside and outside our homes. A smart city also includes a smart grid, providing and transforming electrical power to different areas within a city. IoT also has green applications, such as environmental monitoring and protection using smart solar panels, weather monitoring, water safety, and farming systems. The concept of smart city has been adopted worldwide. Many cities around the world have initiatives and IoT applications within their facilities. Consider the smart transportation within the city of Toronto, Canada. The Toronto Transit Commission, or TTC, provides a real-time map tracking streetcars and bus routes. The tracking using website or mobile app for a quick, convenient, and safe way to get around the city. IEEE has an initiative for smart cities that has been engaging with municipalities around the world to help them in deployment of standards-based solutions. IEEE Standards Association develops standards that are directly related to smart city systems. Here is an overview of the different IEEE IoT standards used within Smart City. This is another reference to explore more. Smart City concept is used to provide citizens an improved quality of life in different areas, including one of the top smart cities in the world. Singapore government launched a Smart Nation vision in 2014. The initiative included a large number of sensors and cameras to be deployed across the island to be used as part of the city IoT ecosystem. The initiative includes different categories of IoT utilization, like urban living, transportation, health, government, and businesses. And each has different projects. Like in urban living, there are different initiatives such as Virtual Singapore. The city is known for the development of software called Virtual Singapore, where a dynamic 3D model that enables the public, businesses, government, and research agencies to develop solutions and run simulations and virtual tests using a large-scale model of the city. A 3D dynamic model that incorporates real-time data from a network of sensors that have been installed across the city. There are also many apps used for accessing different services. Singapore is a world leader when it comes to transportation networks and has investments in road sensors, smart traffic lights, and smart parking. Examples of the different apps used for transportation area: mytransport.sg is a smartphone application provides real-time information for commuters around Singapore. In North America to adopt smart city technology. The city has many smart projects like public transportation network, smart sustainability, and urban development initiatives. It also has one of the highest densities of LEED certified buildings in the United States that helps in reducing energy usage. The city has been a leader in terms of smart parking. The San Francisco Park Initiative, which was launched in 2011, where large number of sensors are used to monitor parking spaces. This gives a real-time information about where parking is available so drivers can quickly find open spaces. Demand-responsive pricing means that the pricing responds to demand. The San Francisco Park app works by using smart pricing. The app periodically adjusts meter and garage pricing up and down to match demand. Demand-responsive pricing encourages drivers to park in underused areas and garages, reducing demand in overused areas. The app works. This course gives an overview of the foundation of Internet of Things. To continue learning about IoT, check out these courses: IoT Foundations, Operating Systems Fundamentals, IoT Foundations, Fundamentals. And if you want to learn more about industrial automation systems, I recommend checking out this course, Learn Industrial Automation, that goes through each level of the automation field. I hope you enjoyed learning about IoT. I look forward to seeing you in another course. Until next time, enjoy learning.